Hello and welcome to the online learning video for chapter 13.6, Quadric surfaces. So first let me note that at the end of this, I will be going over two of the most missed homework problems from 13.5. So if you feel that you want to take a look at that before this lecture, feel free to skip ahead. So this is the last section on the geometry of lines, planes, and surfaces in 3 dimensions. And then in 14.1, we begin calculus with concepts like vector calculus and so on. And this section is important not just for quadric surfaces, but for garnering an ability to visualize surfaces in 3 dimensions, regardless of what their equations might look like. So we actually already learned one quadric surface at the end of the chapter 13.2 lecture. 13.3. We learned the distance formula, and the equation of a sphere. So the equation of a sphere centered at ABC is this guy. And today we're interested in generalizing that kind of thing to other surfaces. So first, the simplest type of surface is a cylinder. And in mathematics, a cylinder, or in higher mathematics rather, a cylinder is not the cylinder that you're thinking of. It is any surface that is parallel to a line. So these two guys are examples of cylinders. And a traditional cylinder is, in this definition, a type of cylinder. Traditional cylinder meaning this guy that you're probably all visualizing when you hear the word cylinder. In a traditional cylinder, the entire surface is all parallel to a vertical line in this case. And in this cylinder, the entire surface is all parallel to the z-axis, as you can see. And in this cylinder, the surface is parallel everywhere to the x-axis. So let's identify and describe the following surface. X squared plus y squared equals 1. Now I may look at this and think, oh, that's a circle. But z is also a variable here in 3 dimensions. Okay, so this surface, x squared plus y squared equals 1, is on the xy plane a circle centered at the origin of radius 1, as you'll all recall. And it does not care what z is. So regardless of our z value, it is still a circle. It's in particular a circle that is parallel to the xy plane. So visualizing this, here is our x, y, and z axis. So on the xy axis, this is a circle of radius 1, but it does not care what z is. So for any other z, it is still a circle of radius 1. the circle of radius 1 for any z, since z isn't even in the equation, so no matter what z is, it satisfies it. And you can see that, therefore, this is a traditional cylinder. It's a vertical cylinder around the z-axis of unbounded height. So that's the type of thinking that we'll be needing to do with equations in 3 dimensions. And again, this is a cylinder in our more generalized definition, because everywhere the surface is parallel to the vertical line that is the z-axis. What about y squared plus c squared equals 1? Take a moment to think about this. Pause the video if you want, and try to find what it is, given the process that we just did. Okay, so on the YZ plane, this is again a circle of radius 1, and it still is for any x, because it doesn't care what x is. And let me point out, the way to really think about this is for any x equals x naught a constant. So imagine a constant x, then for that constant x value, this is a circle. So on our x, y, z, this is a circle of radius 1. On the YZ plane. So like that. There, my attempt at 3 dimensions. And no matter what x is, it is still a circle of radius 1. So this is a cylinder of, again, unbounded height around the x-axis. Or length, rather, in this case. So this is a cylinder of radius 1 around the x-axis. Now, we're going to be using the surface, pardon me, I got something in my throat. The conic sections that you learned about in a previous class, or should have, such as ellipses, parabolas, and hyperbolas, and I will be doing a review of those as we go through. So first, recall that the equation of an ellipse centered at the origin is x squared over a squared plus y squared over b squared is 1, where a is the radius in the x direction and b is the radius in the y direction. So it looks like this. And if we forget this, we can find what we'll call the traces of the ellipse on the x and y axes. So for example, plugging in x equals 0 to find the y values when x equals 0, then we have 0 squared over a squared plus y squared over b squared is 1, which means that y squared is b squared, which means that y is plus or minus b. Remember that when we take the square root of of both sides, it's actually a plus or minus square root, because a negative number squared is also positive. And that plus or minus b for y is these two guys. That's b, that's minus b. So this is a trace in 2 dimensions, and in a bit we'll be doing traces in 3 dimensions to be able to understand and visualize surfaces in 3 dimensions. And also recall that we can translate over figures to have different centers or the like. So to translate an ellipse to have center x naught, y naught, we just replace x with x minus x naught and y with y minus y naught. And that works for any function whatsoever. And the reason that that works is that now for an x and y to satisfy this equation, x must be x naught bigger than it was, since we're subtracting x naught from it, and y must be y naught bigger than it was for the same reason. So therefore the new center is at x naught, y naught, since we have shifted x naught to the right and shifted y naught up to satisfy the same equation. So that's the center, that's the new center. And as you know, the standard form of a parabola, center at the origin, the meaning vertex at the origin, is y equals a squared, or x equals ay squared. So I meant to say y equals ax squared. I think I mispronounced. So y equals a squared, that is our standard parabola. That looks like this. And if we swap x and y, then it looks like that. Sideways parabola. It's just that now think of it as that x is the output and y is the input. And in the same way, to translate a parabola to have center, again by center here we mean vertex x naught, y naught. We do the usual replacement of replacing y with y minus naught, y naught, and replacing x with x minus x naught. In either form, whether it's an upward facing parabola or a sideways facing parabola. And the last conic section, that is everyone's least favorite, likely, is the hyperbola. So an ellipse is of the form x squared over a squared plus y squared over b squared is 1. In a hyperbola, we replace that with a minus sign. And the minus sign can be either attached to the y squared or it can be attached to the x squared. And that different attachment affects whether the hyperbola is facing sideways or the hyperbola is facing upwards. And once again, if we forget the orientation, and I often do, we can just find the traces of the ellipse of the hyperbola on the x and y axes. So I mentioned that I forget which one is which as far as orientation is concerned, but with some practice, you can equally well mentally quickly find the orientation through a trace like this. So for example, plugging in x equals 0 to x squared over a squared minus y squared over b squared equals 1 is negative y squared over b squared is 1. And what's the solution to this? Well, this guy is negative, while 1 is positive. And that means no solution. Okay, have we made a mistake? No, we have not. That no solution corresponds to this picture. Here's the y-axis, here's the x-axis. And when x equals 0, then that is the y-axis. And the hyperbola has no intersection with the y-axis. So in other words, there truly is no solution, no point on this parabola that satisfies x equals 0, since there is nothing on the y-axis. And therefore, we can identify it can't possibly be facing upwards. Otherwise, there would be two solutions on the y-axis. So it must be facing sideways. And personally, I do have to quickly think through this process every time to identify which one is which. And again, negative y squared is always negative because y squared is positive. That was the inference here, how we got that is always negative. Or 0 if y is 0, but also 0 is not 1. So let's do an example. So y squared over 4 minus x squared over 9 is 1. And we'll do this with traces. And here traces mean that we can plug in x equals 0 or y equals 0. So if y equals 0, then we have 0 squared over 4 minus x squared over 9 is 1, which implies negative x squared over 9 is 1. Okay, this guy is as before negative, or 0, while this guy is positive, and that means no solution. And y equals 0 corresponds to the x-axis. So the hyperbola can't possibly be facing this way, where there would be these two solutions. So therefore, we know that the parabola must be facing this way. And we're interested in what are these 2 points? Well, those 2 points correspond to x equals 0, since the y-axis is x equals 0. So we can find those by plugging in x equals 0 into the equation and solving. So if x equals 0, then we have y squared over 4 minus 0 squared over 9 is 1, which means that y squared is 4, which means that y is plus or minus 2. Again, when we take the square root, it's plus or minus, recall. Okay, so plus or minus 2 is the y-intercept when x equals 0. And from the first part, we already figured out that it must be facing up down. So our hyperbola looks something like this. And yes, it also has slant asymptotes that is approaching. And we can find those, well, we don't really care about them, not in this class at least. Okay, so we have these 2 forms of the equation of hyperbola. And again, we can shift them to have a different center other than the origin, with the usual replacement of x with x minus x naught, etc. So in these, we have been utilizing what we've been calling traces. A trace meaning plugging in or setting one of the variables to be constant to see what a sort of slice of our two-dimensional equation looks like. So in this case, one of the slices is the y-axis, and we found that y-axis by plugging in x equals 0 and found what the hyperbola looks like on that slice, which is these 2 points. Except now a slice in 3 dimensions will be a whole line or curve in 2 dimensions. So there's the xy trace. Again, traces meaning these slices. So here's an example figure in 3 dimensions, a surface. So if we set z equals 0, then we are on the xy plane. And in this case, it looks like we'd get an ellipse or a circle on the xy plane. And that is called the xy trace. Similarly, setting x equals 0, now we're on the yz plane. And it looks like for this figure, the resulting equation would be that of a parabola. And similarly, the xz trace, setting y equals 0 in the equation, it looks like it'll yield a parabola. And our idea for visualizing equations in 3 dimensions will be to take these slices and then put the puzzle pieces together. So we know it's elliptical horizontally and parabolic vertically. And therefore, we can piece those together and get that this is the overall surface that we see here. So let's do an example. Let's find the xy, xz, and yz traces of this surface and use that to describe the surface. So when z is 0, which will give us the xy trace, so we plug that in, and we have x squared over 4 plus y squared over 9 is 1. Again, our z here is 0, so it goes away. And we already know that that is an ellipse. Similarly, the xz trace, that means that we set y equals 0, and we have x squared over 4 plus z squared over 16 is 1. There is no y since y is 0, and again, that is an ellipse. And as you can see, due to the equation symmetry, for the yz trace, well, that means we plug in x equals 0, and then y squared over 9 plus z squared over 16 is 1, again an ellipse. So all slices, xy, xz, and yz are ellipses, and we can put those together and see that it must be a figure that looks something like this. So for example, this guy here was our xz trace, which was an ellipse as we found. This guy here was our xy trace. Etc. And for each of these traces, if we wanted to visualize it more specifically, we could have found, for example, that here the x radius is 2 and the y radius is 3. Using our knowledge that the x and y radii of the ellipse, respectively, squared are these guys. 2 squared is 4, 3 squared is 9. And this would allow us, if we wanted to graph or visualize this ellipsoid, as we'll call it more specifically. Again, this is just what this ellipse specifically is, using our knowledge of what these numbers correspond to. So from that, we know it's x radius 2, y radius 3, and we could do the same thing with a different trace that we found and find the z radius is 4. Okay, I call this xz, depending on the graphing orientation. That's more typically y. The axes here are not labeled though, so doesn't matter too much. So here is another surface, and these are just in-depth examples of its various traces with visualization, which I can't draw very well, so that's why I've included it. So for this guy, oh, and also, so an important thing is, so far we have been finding exclusively x, y, x, z, and y, z traces, but we can generalize this to other traces. So for example, instead of setting z equals 0 to find the x, y trace, we could just imagine that z is a constant. So take a look here. So you see that they're setting z equals z naught. That means that we're imagining z is a constant. And that constant could be anything. So z naught is perhaps here an arbitrary point on the z-axis. And for that constant z naught, it becomes the equation of an ellipse. So we know that every horizontal slice is that of an ellipse. To see that this is an ellipse, just imagine dividing both sides by z naught, and it's in the form of an ellipse. X squared over something plus y squared over something is 1 after we divide both sides by z naught. And furthermore, we can see that the higher z naught is on the z-axis, then the larger the radii, since we're dividing by a bigger number, increasing those denominators. And the radii in the x and y directions squared are those denominators of x squared and y squared, respectively. Okay, similarly, we can find all traces parallel to the yz plane by setting x to be an arbitrary constant. And here, if we imagine that x is constant, so now it's x naught, that's constant, then it becomes z is c plus y squared over 4, which is a parabola. It's like ay squared plus b, however you want to think of it. So we have various parabolae horizontal to the yz plane. Similarly with the xz plane. Okay, so now we can take our various traces and put them together, and we can get that it must look like this shape. So here is a visualization of all of our traces put together on the right. So let's do an example. By substituting x equals x naught, in other words, imagining x to be a constant, and then in different steps, these guys, let's find the 3 traces of this equation. Okay, for clarity, I type this out. So if we imagine that x is a constant, then the equation becomes this. That looks a bit different. All we did is moved the x naught squared over 4 to the other side, subtracting it from both sides. So this right-hand side is a constant. So this is like y squared minus c squared is 1 if we were to divide the right-hand side or both sides by the right-hand side to get it to be equal to 1. And of course over a squared and over b squared, whatever those are. And that is the equation of a hyperbola, as we know. Similarly, with setting y equals y naught, now this guy becomes constant, move it to the other side, and we have this, which is once again a hyperbola. It's like x squared over a squared minus c squared over b squared is 1, after we divide both sides by the right-hand side to get it to be 1. And finally, if z is constant, then this guy is constant, add it to both sides to move it to the other side, and we get this. So this is like x squared over a squared plus y squared over b squared is 1. Again, after we divide both sides by the right-hand side to get it equal to 1. And that is the form of an ellipse. Now, let's take a moment and visualize this. And I encourage you to pause the video, try to visualize this hyperbola and also hyperbola on the xy plane and also on the yz plane and also on the xz plane. And then on the xy plane, an ellipse. Try to think about what 3D shape could have those slices or traces. Pause the video if you want. So, well, this is the shape. XZ traces, as we found, are hyperbolas. Same with the YZ traces, while all of the XY traces, that is setting, all of the XY traces, that is setting Z to be a constant, those were all ellipses, as we found. So hyperbola, hyperbola, and ellipses, and this is the shape. This is called a hyperboloid of one sheet. At the end of this lecture, I'll give all of the quadric surfaces, as they're called, with their names. Right now, we're focusing on slices, traces, and visualizing them from those traces. Let's do another example. I encourage you to pause the video and try your hand at finding these traces yourself and identifying which conic section each of those traces is. Okay, so if x is constant, then it becomes this. And those are parabolas. It's just z is c minus ay squared, classic parabola. When y is constant, which is another one of the vertical traces, the xz plane, and things parallel to it, then it becomes this. Once again, parabolas. That's c equals x squared minus c for c a constant. And when z is constant, then it becomes this. I've just swapped the left and right hand side, same thing. And look at that, those are hyperbolas. Dividing both sides by z naught, we get x squared over a squared minus y squared over b squared is 1. And in particular, those are hyperbolas. well, when z is positive, their hyperbolas oriented outward along the x-axis. But notice that when z is negative, then we have to divide both sides by a negative number, swapping x and y, and the hyperbolas are oriented going outward along the y-axis. I point that out here. So when z is negative, say z equals -1, then it looks like this, equals -1, and then dividing both sides by -1, it swaps the x and y. So that means that between the positive and negative horizontal slices, when z is constant, that's a horizontal slice, the hyperbolas switch direction. Okay, so we have vertical slices of parabolas and horizontal slices of hyperbolas that switch direction as we pass from positive z to negative z. What could that look like? Again, pause the video. I encourage, try to think of what that could look like. Okay, so we know that the hyperbolas switch direction from being oriented outward along the x-axis to being oriented outward along the y-axis when z switches from positive to negative. So something like that. Okay, and we know that we have parabolas both on the yz plane and on the xz plane. So putting the pieces together, we arrive at this shape. We'll call it a hyperbolic paraboloid. Again, I'll go over all of these names near the end. Sometimes we'll need to complete the square. We did an example like this when we first introduced spheres back in 13.3. So recall that to complete the square, so x squared plus a squared, we add a over 2 squared and also subtract it, which is the same as doing nothing in a fancy way. And then this guy, inside those big parentheses, factors is this. And that completes the square. So in this case, let's complete the square. So we have -16 times x squared minus 4x minus 4y squared plus z squared equals 80. So all I did here was, so I gathered the 64x with the -16x squared, and then factored out a -16, and 64 over -16 is -4. Okay, now we can complete the square here. So we have x squared minus 4x plus 4 minus 4. Okay, so this is our a. This is a over 2 squared. So is that. We add and subtract a over 2 squared, and then put parentheses around that. And this guy factors as a square. It's x minus 2 quantity squared. Okay, and then we still have the rest. Okay, so we have -16 times x minus 2 quantity squared minus 4 minus 4y squared plus z squared is 80. So -16 x minus 2 squared plus 64 minus 4y squared plus z squared is 80. Okay, almost there. Now let's get this 64 on the other side. 80 minus 64 is 16. So we have minus 16 x minus 2 squared minus 4y squared plus z squared equals 16, as are subtracting 64 from both sides. And finally, to get it into a standard form, let's divide both sides by 16. And we have negative x minus 2 squared minus y squared over 4 plus z squared over 16 is 1. Okay, we did it. That is now in a standard form of one of our quadric surfaces. We don't know which one, but we can now easily, well, as easy as traces can be, we can, if we understand them, we can easily take traces of this and put together the pieces to identify what it is. So looking at this, I'm going to say this verbally, and this is how I personally, and you can too, quickly identify the general shape. So I just imagine, okay, when z is 0, we have negative numbers. Negative squared is positive. So when z is 0, there can be nothing, no solution. When y is 0, we have a hyperbola. And when x is 0, we have a hyperbola. Okay, so there is no solution when x is 0. So that means that the shape must begin, sorry, no solution when z is 0, I mean. So that means that the shape must begin when z is non-zero, symmetrically up and down. And then we have hyperbolas on both of these planes. So those are our two hyperbolas. And so we said that when z is 0, then there's no solution. However, when z is big enough, then when we subtract it from both sides, this becomes negative, multiply both sides by that negative number, and it becomes an ellipse. So we then have ellipses when z is big enough. So our shape looks like this, if you can decipher my chicken scratch attempt at 3D shapes. It's like a cup facing upwards here, and symmetrically a cup facing downwards here. So I know that was all verbal, but hopefully it's a good illustration of where you can get to once you really understand traces, and you can see how I was able to piece this together and visualize it mentally, really. So that's the goal, I guess. Oh, so here's the in-depth work of everything that just went on in my head. Because I already said all of this, I'm not going to say it again. But you can certainly pause and look through that. If it was hard to follow what I was saying. Okay, so here's the ultimate shape. This is the same shape that I drew over here, except better drawn, of course. And this is called a hyperboloid of two sheets, these two being the two sheets. And we could even find the vertices through traces if we wanted to be super specific, but that doesn't matter much. Hey, so here's our glossary of surfaces. We are now done with the section, aside from giving names to all of these guys that we have found. So this guy that we began with is an ellipsoid, and the traces are all ellipses. Looks like that. Something of this form is an elliptic paraboloid. Two traces are parabolas, namely that parabola and that parabola. And the other traces are ellipses. So that's our ellipse trace. This guy, which is like an ellipsoid but with one minus sign, is a hyperboloid of one sheet. And two traces are hyperbolas. Okay, there is one hyperbola, the other is, I'm not going to try to draw. So the two traces are hyperbolas, and one trace is an ellipse. So all of these guys are ellipses. And here it does have a solution when z is 0, as you can see, because that just goes away, and that's an ellipse. Okay, however, if we have two minus signs in our kind of modified equation of an ellipsoid, then that becomes a hyperboloid of two sheets. So it's like, imagine this getting thinner and thinner until it's a point and then separates. That's a hyperboloid of two sheets. So here, two traces are hyperbolas. So for example, that there in blue is one of the hyperbola traces. And one trace is an ellipse, namely that's an ellipse or that's an ellipse, but only for certain values of z. So this is the example that we recently did. When z is 0 here, there's no solution. It's negative squares equals positive. That's impossible. But when z is big enough in either direction, then we're doing 1 minus z squared over c squared, which can make the right-hand side negative. And then we have negative equals negative exists as a solution. And that solution is an ellipse. Okay, and so I just mentioned the kind of in-between state. So if we imagine stretching this as this part increasingly pinches off and gets smaller and smaller, when it's a single point, then we get this shape. This is just before a hyperboloid of two sheets separates, sorry, a hyperboloid of one sheet separates into a hyperboloid of two sheets. So this occurs when in this equation, this 1 becomes 0, and then the z squared is moved to the other side, and it is that. This is called an elliptic cone. Two traces are hyperbolas or intersecting lines. So this is one such hyperbola. A hyperbola needs the other side to be non-zero. If the other side is 0 in the equation for a hyperbola, so in other words, instead of equals 1, it's equal to 0, then it becomes two intersecting lines. Let's illustrate that here. If y equals 0, then we have x squared over a squared is z squared over c squared, which implies that z is equal to plus or minus c over a x. Multiplying both sides by c squared and taking the square root of both sides, not forgetting the plus or minus sign. Those are just lines. It's two intersecting lines, depending upon the plus or minus. So that xz trace when y is 0 is those two intersecting lines. And one trace is ellipses. When z is constant, then that's the standard equation of an ellipse. Being those guys. And finally, a hyperbolic paraboloid. We also did this example, looks like that. One trace is hyperbolas when z is constant. These are the ones where the hyperbolas switch orientation depending upon if z is positive or negative. You'll recall that example. And the other two traces are parabolas. So that concludes 13.6. The rest is, well, this is just a final example. I won't verbally go through it, I've said enough, but you can take a look at that and try your hand at it and verify what you get. And then pause this video and try to think of what the surface looks like. And again, as always, I encourage you not to memorize these equations that we just saw, unless you can, but it's not necessary. And it's better, I would argue, for you to instead be able to do the kind of thing I did over here, where I was able to mentally see what this looks like through mentally taking traces. That's the goal. It is how to think about math, and it is so helpful in a class like this. Yeah, so try your hand at that. Pause the video now if you want. Okay, there are the traces, and pause if you want, and that's the shape. So that was our elliptical cone. Okay, we're done. Now, as I said at the beginning of this lecture, we're just going to go over two of the traditionally most missed homework problems from the 13.4, 13.5 homework. So here's one. We're given two lines. We want to determine if they're parallel, intersect at a single point, or skew. Skew meaning that they're neither parallel nor intersect. So first, are these lines parallel? Well, remember that this is the vector v corresponding to the direction of that line. And this is the vector, we'll call it w, corresponding to the direction of that line. So what we want to ask is v equal, question mark, to c times w? That is two vectors being parallel. Okay, so that's asking is 5 minus 9 minus 1 equal to c times 2 minus 2, 5. Okay, well, if so, that means that setting the first coordinates equal, 5 must be 2c. Okay, again, that's setting the first coordinates equal. 5 is equal to c times 2. So c is 5 halves. But setting the second coordinates equal, 9 is not equal to 5 halves times minus 2. Let me color code this. This came from setting the first coordinates equal. And this came from then setting the second coordinates equal. So what we found is no, not parallel. Do they intersect? Okay, well, if so, then for some t and s, r of t must be equal, little r of t must be equal to big R of s. Different t's give different points on this line, and every point on the line corresponds to some t. So if they intersect, then there must be some point on that line, some t, that gives a point on the line equal to a point on this line corresponding to some s. So we write out this equation and try to solve for s and t. If we can find a solution, then we find the point of intersection. And if we can't find, if there is no solution, so in other words, the system of equations that we'll get is contradictory, then the lines must be skew since they're not parallel and don't intersect. Oops. Okay, so we're doing R of t, little r of t is big R of s. That is 5 to 3 plus t times 5 minus 9 minus 1 is equal to the right-hand side. Okay, I'm not going to finish writing that out. Now, we want to distribute. So we have 5, distribute the t and add together the vectors. We have 5 plus 5t, comma, minus, comma, 2 minus 9t, comma, 3 minus t must be equal to 9 plus 2s minus 2 minus 2s, 13 minus 5s. So again, this whole guy is our R of t, just distributing the t and adding the vectors. And this whole guy is similarly our big R of s, distributing the s to the components and adding the vectors component-wise. Now, if two vectors are equal, their components must be equal to each other. So this is the same as the system of equations. 5 plus 5t is 9 plus 2s. 2 minus 9t is minus 2 minus 2s. And 3 minus t is 13 minus 5s. Oops. Okay, this is what I was checking. That's s times positive 5. I accidentally wrote a negative there. Okay, so we want to solve this system of equations and see if it has any solution. So we can do this by, among other techniques, standard substitution. But what I'm going to do is the elimination method. So notice that this has a plus 2s, this has a minus 2s. Let's add these equations together. And what do we get? We have 7 minus 4t is equal to 7. 5 plus 2 is 7. 5t minus 9t is minus 4t. 9 minus 2 is 7. And 2s minus 2s goes away. So if you can do elimination like this, it's much quicker. This means that very conveniently, t is equal to 0. Subtracting 7 from both sides and dividing both sides by negative 4. Okay, super convenient. So now let's solve for s. We can plug this back into one of the equations, say equation 1. Why not? Then we have 5 plus 5 times 0 is 9 plus 2s, which means that s is equal to -2. Okay, so we got t, we got s. Now, what could happen in some circumstances is that, so notice that we got t and s exclusively from the first two equations. This third equation we have not touched. In some circumstances, now if we plug our t and s values into the third equation, it would not satisfy it. If it does not satisfy it, that means there is no solution to the system and thus no point of intersection. So the lines must be parallel or askew. And if they're not parallel, as we already found, then they would be skew. So now let's plug these into equation 3. And we have 3 minus 0 is 13 plus 5 times -2. We're asking if is that true, really? And look at what we get. 3 is 3. So that means that t equals 0 and s is -2 is a solution. So the lines intersect at a single point. The problem also asks us, though, to determine the point of intersection if they do. Okay, well, that point of intersection occurs when t equals 0 in the first equation, or occurs when s equals -2 in the second equation. So to find that point, we can just plug in t equals 0 to r of t, or we can plug in s equals -2 to big R of s. No matter which one we'll do, we'll get the same point either way, since it's a point of intersection after all. Let me color code again. So plugging in t equals 0 to equation 1, we have 5, 2, 3 plus 0 is 5, 2, 3 is our point of intersection. Or just to demonstrate, we can equally well plug in -2 into r, and we have 9 minus 2, 13, plus -2 times 2 minus 2, 5. Okay, 9 minus 4 is 5, minus 2 plus 4 is 2, and 13 minus 10 is 3. So either way, we get the same point. That is the point of intersection. Okay, and the last one we'll go over, the other most missed homework problem, is this one. Find the distance from this point to that line. Now, I think that the main thing that might have thrown people off here is just that this line is not in vector form, it's in parametric form. However, this line, we can easily convert from parametric to vector form as follows. So this is the same as x, y, z, sticking it in a vector, is equal to minus 2 plus 2t, comma, minus 4 plus t, comma, 6 minus 3t. This is an arbitrary point on the line. We'll call it r of t. And then in this guy, writing it as a sum of two vectors, that's negative 2, comma, negative 4, comma, 6. Is equal to, or plus 2t, comma, t, comma, minus 3t. And that's negative 2, negative 4, 6, plus t times 2, 1, minus 3. Okay, so now we have it in the form r of t equals r naught plus tv, and that's our equation of the line. And now that it's in a standard form of a vector equation of a line, it's just a matter of plugging it in to our formula for the distance from a point to a line. Okay, so we now have all the ingredients that we need. This is our point Q. 1, 4, minus 4. And we have that r of t is minus 2, minus 4, 6, plus t times 2, 1, minus 3. So that's our Q, that's our V, and this is a point P on the line. That's always a point P on the line, just plugging in t equals 0, that goes away, that's a point on the line. Okay, so now we know that PQ, that's Q minus P. Is 3, 8, negative 10. Well, now V cross PQ. We stick it in our matrix and find the determinant. That is 2, 1, negative 3. 3, 8, negative 10. And ijk. And that is this. Again, review my lecture on cross products if this is unfamiliar, how we're doing this. So that was expanding along the last row. And for each of these, we delete the row and column in which that ij or k resides and find the determinant of that submatrix. Okay, so that is, so 1 times minus 10 minus 3 times 8 is negative 10 plus 24 is 14. So we have 14i. Here we have 2 times minus 10 is negative 20, minus negative 3 times 3 is negative 11. And a minus sign, that's positive 11, j. And here we have 2 times 8 minus 3 times 1 is 13. Okay, so what we want is not the cross product itself, but its magnitude. Okay, so we want the magnitude of 14, 11, 13, which is the square root of some of the squares of those guys, which is 9 root 6. I'll skip some arithmetic steps there. We can all do arithmetic. You have a factor of 3 squared under the square root, sorry, 9 squared under the square root, and you can pull it out. And we also want in the denominator the magnitude of v. That was the magnitude of 2, 1, negative 3. Which is the square root of 14. So finally, d is therefore 9 root 6 over root 14. We can simplify that slightly. That's 9 times root 2 times root 3 over root 2 times root 7. Just factoring each of those guys. Those guys go away. And now multiplying it by root 7 over root 7, we have that this is 9 root 21 over 7. Have a great one, and next section we'll begin actual calculus on vectors and curves in space and the like.